Hello everyone. I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, Aligarh Muslim University. This lecture is in continuation to our discussions on simultaneous equation models, and today we will be basically we will be referring to the methods by which we can solve simultaneous equation models. There is an issue because of which your simple OLS cannot be used over here in simultaneous equation models, except for one system of model which is called as recursive model, where if you satisfy certain conditions and your model is in the form of recursive models, then we can use OLS. But apart from that, we cannot use OLS. The idea behind this concept is like we estimate a demand function, that is QD is equal to B naught plus B1P plus B2P naught plus B3Y plus U, where your P is the price of the commodity and P naught is the price of other commodities, Y is your income and U is the random variable. But if we apply OLS over here, we will get the biased estimates of B naught and B1, as price and the random term U or the error term U are not independent. The demand for any commodity is a function of its prices, but at the same time, price is in the market is also influenced by the quantity demanded. If the demand is very high, the producer class or the seller class will increase the price of it. So consequently, this equation, that is the simple demand equation, it cannot be treated as a complete entity. There should be at least one more equation over here, like we have stated another equation. P is equal to C naught plus C1Q plus C2W, wherein W is your weather. Supply depends upon weather conditions, we can say, particularly of agricultural products. So now if we substitute this element, this price function over here, we can write the equation P is equal to C naught plus in the bracket B naught plus B1P plus B2P naught plus B3Y plus U. This was basically the price function, plus C2W plus V, means you are it's the way round, means we are incorporating all the elements over here. Now, obviously P is dependent on U, and hence it violates the assumption that U is independent of the explanatory variable. That is, P is not exogenous to the demand function. So since P is not exogenous to the demand function, this is a violation of the expected value of U and X, that is error and the independent term or the explanatory term, which we have assumed in classical linear regression model to be 0. Here it will not be 0. We give a quick proof that how come this covariance of X and U, that is the independent variable or the exogenous variable over here or the explanatory variable over here, is related with your error term. So let us take an equation Y is equal to B naught plus B1X and X is equal to A naught plus A1Y plus A2Z plus V. V is the error term. Now the error term, expected value of U is equal to 0, expected value of V is also equal to 0. Expected value of U square is equal to your sigma square, that is the variance is constant, and expected value of V square, that is the variance of the error term V in the X equation, is sigma U, that is also constant. And we also assume that the errors are not related, that expected value of Ui, Uj is 0 and expected value of Vi and Vj, that is the consecutive error terms, are not related with each other. Now we have the two equations, 1 and 2. This is equation 1 and this is equation 2. We are substituting equation 1 in equation 2. So now what we have this equation of y. We substitute, this is nothing but my y is equal to b naught plus b1 x plus u. We are inserting it into the x equation. So x equation becomes x is equal to a naught plus a1 in bracket b naught plus b1 x plus u bracket close plus a2z plus v. Now we open the brackets and insert this a term inside the bracket, that is you get x is equal to a naught plus a1 b0 plus a1 b1 x plus a1 u plus a2z plus v. Now we take the x term to the left hand side of the equation. So we have x minus a1 b1 x plus a naught plus a1 b naught plus a1 u plus a2z plus v. Now in the left hand side what we do, we take x common. The moment we take x common, so we have x bracket open 1 minus a1 b1 is equal to a naught plus a1 b naught plus a1 u plus a2z plus v. Now this term, that is 1 minus a1 b1, we take it to the right hand side as the denominator, so all the terms on the right hand side are divided by this term a1 b1. So we have x is equal to a naught divided by 1 minus a1 b1 plus a1 b naught divided by 1 minus a1 b1 plus a1 u divided by 1 minus a1 b1 plus a2z divided by 1 minus a1 b1 plus v divided by 1 minus a1 b1. Now here certain things are so then finally what we do, we can write it in this format, the last equation. So finally we write it in the format of the last equation, that is x is equal to, we combine the terms. We combine the terms and we can say x is equal to a naught plus a1 b naught divided by 1 minus a1 b1. It means we have combined the first two terms together. Then we have a2 divided by 1 minus a1 b1 z, that is we have taken this term in the equation. In the second last equation, we have taken the fourth term to be the middle term over in the last equation, and then we have merged these two, that is a1u, because it has an element of u which is an error term, and the last term is also v, having v divided by 1 minus a1 b1. So both u and v are the error terms. So we combine these two. So what we have finally in the third term is v plus a1u divided by 1 minus a1 b1. So this is the third equation which we have got after inserting the value of y in x, the equation of x. So now what we do is we are trying to prove that x and u are correlated, that is the independent variable and u are correlated, and x is, meaning if they are related, then x is not exogenous. So for that proof, we see the formula for covariance is expected value bracket open u minus expected value of u divided bracket closed, another bracket opens x minus expected value of x, then the entire bracket closes. Now expected value of u by assumption is equal to 0. Expected value of u is 0. So the covariance formula can be written as expected value of u bracket open x minus ex, means from the first term this eu it gets 0, so what is left is only u, and the second term remains as it is, that is x minus expected value of x. Now just in our previous discussion we have got the value of x, that is x is equal to a naught plus a1 b naught divided by 1 minus a1 b1 plus a2z divided by 1 minus a1 b1 plus v plus a1 u divided by 1 minus a1 b1. Now what will be the expected value of this term? So if we are going to take the expectation of this, In the first term, there are constant terms a1 and a1, b0 and all these are there. In the second term also there are constants a2. So those will remain even when we take the expectation. But the last term, it has error v, u, and expected value of the error we have seen by the assumption they are equal to 0. So the last term of x, that is in x there were three terms, the last term of x which has an v and u component, if we take the expectation that would become 0. So we are left with, when we are taking the expectation, we are left with only a0 plus b0 a1 divided by 1 minus b1 a1 plus a2 divided by 1 minus b1 z. Means, so in this equation we have what is to be inserted in place of x, and we also have what is to be inserted in place of expected x. So using this information, we go on to define the term x minus expected value of x. So we have a0 b0 a1 divided by 1 minus b1 a1 plus a2z divided by 1 minus b1 a1 plus a1u plus v divided by 1 minus b1 a1 minus, now we will take the expectation of x, that is equal to a0 b0 a1 divided by 1 minus b1 a1 plus a2z divided by 1 minus b1 a1. Now when we open the bracket, the sign would change of the expected of x. So one of the terms it becomes minus, and the other term also, both the terms it becomes minus. So when it becomes minus, then we see, when we open the brackets, we find that the first term which is highlighted in yellow and the another term which is also highlighted in yellow, they are the same but with different opposite signs, so they can be cancelled. And again the ones which are highlighted with green color, that is a2z divided by 1 minus b1 a1, and another term is of the same, with the same numbers, digits, but the negative sign, so these green terms also cancelled. So for the component x minus expected value of x, we are left with only a1u plus v divided by 1 minus b1 v1. So we got the term of x, and what was our covariance? We have to multiply this with u. So our covariance ux is equal to, as we have seen before, expected value of u multiplied by x minus ex. So x minus ex we have just now derived is equal to a1u plus v divided by 1 minus b1 v1. Then for finding the covariance of x and u, we multiply with u. Upon multiplication, we are supposed to find the expectation of ua1u plus uv divided by 1 minus b1 v1. So now what we do, we take expectations, because in the denominator there is all the terms are constant, we take only expectations in the numerator. So expected value of a1u square plus uv divided by 1 minus b1 a1. Now there are two terms over here, a1u square and uv, we separate them. So we find expected value of a1u square divided by 1 minus b1 a1 plus the second term, that is uv divided by 1 minus b1 a1. Now we can take out 1 divided by 1 minus b1 outside as a common factor multiplied with expected value of a1u square plus uv. This we can, since expected value of uv, u and v both are error terms, so the expected value of them will be 0. So what we are left with is 1 divided by 1 minus b1 a1 expected value of a1u square. Now this term, now also we can take outside a1. So finally we write it, this is a1 divided by, please note the correction over here, it's a1 divided by 1 minus b1 a1 multiplied by expected value of u square. Now this term is not 0. This term is not equal to 0. You have this constant a, b and also u square. So if this is not equal to 0, it means covariance of xy, covariance between the independent regressor, that is x, or the exogenous variable x and u is not equal to 0. So if OLS is applied, the estimates will not be unbiased, the estimates would be biased and inconsistent. So because of this issue, the problems which are created are the identifications. We have the issue with the identification and we have the problem of estimation. Now, we have different methods to be applied in the cases of simultaneous equation models apart from OLS, and those are, means OLS we cannot apply except for that recursive model. Now, the first method which we are going to study is indirect least squares method. We also call it ILS. So, we take a structural model, Ct is equal to alpha plus beta yt plus ut, and yt is equal to Ct plus it. We take a structural model, and we are by now clear that if we use OLS, our beta estimator of beta, the beta hat, it will be biased and inconsistent. But the way out is we can estimate it indirectly. That is, first we obtain the reduced form of the model. In the reduced form, there is no correlation between Ct there is no correlation between Ct and the error term, and Ct is a function of it and yt is a function of it. Then we apply OLS and estimate. We will see the process. So the first step is we find the reduced form. So we have this equation, Ct is equal to alpha plus beta. Now we have our identity equation is yt is equal to Ct plus it. So we insert it over here. So Ct is equal to alpha plus beta Ct plus it plus ut. Now we have Ct is equal to alpha plus bct plus bit plus ut. We take the C term from the right hand side of the equation to the left hand side. So Ct minus bct is equal to alpha plus bit plus ut. We take Ct as common, and in the bracket 1 minus beta is equal to alpha plus beta it plus ut. Now we can take this common term 1 minus beta to the right hand side and as the denominator. So Ct is equal to alpha divided by 1 minus beta plus beta 1 minus beta it plus 1 divided by 1 minus beta ut. Now beta divided by 1 minus beta, that is this the coefficient of this reduced form model, is nothing but summation small c I divided by summation I summation I square. There is again a correction in this term, so it should be summation ci divided, it is written as summation ctit divided by it, but we are just reading it summation ci divided by I square. So the denominator, it should be present in the square. This in the form of moments we can write it as, we have seen this process of moment when we are discussing in our initial lectures of structural simultaneous equation model. So we have seen that MCI, the moment Ci divided by moment II. So we have found this reduced form for the Ct. Now we do the similar operation for the function of yt. Yt is equal to alpha plus beta yt plus it plus ut. You take the yt terms to the left hand side. We try to combine them together. So we have yt minus beta yt is equal to alpha plus it plus ut. I take yt common out. So yt bracket open 1 minus beta is equal to alpha plus it plus ut. So yt can, this term 1 minus beta can be taken to the right hand side and in the form of in the denominator. So yt is equal to alpha divided by 1 minus beta plus 1 upon 1 minus beta it plus 1 upon 1 minus beta ut. Again, this coefficient of it over here, that is 1 upon 1 minus beta, we can write it as summation yi divided by summation I. Again, the square term is missing over here in the PowerPoint presentation. We need to have a square sign. So it is summation it divided by summation it square, and this is equal to, we can in the term of moments we can write myi divided by mii. So once you have done this is basically the first step, and we have formed the reduced form, then we can estimate this by OLS. Estimating this equation, the structural equation, we cannot estimate by OLS, but this reduced form model, in the reduced form equation, can be estimated by OLS. Now see, beta hat 1 minus beta hat, we have seen just now, is equal to, again all the square signs are missing, so it is equal to summation Ci divided by summation I square is equal to MCi divided by MIi, and 1 upon 1 minus beta is equal to summation Yi divided by summation I square, the square term is missing in the PPT, is equal to MYi divided by MIi. Now, so and we have seen earlier that what is beta hat? Beta hat, you can write it as MCi divided by MYi. We can write the beta hat like this. And here we have MCi, here we have MCi and MIi, and from 1 upon 1 minus beta we have formed MYi divided by M11. Now if we just reverse it and multiply, that is, we do the calculation for MIi MIy multiplied by MCi divided by M11 MIi. So what we have done, we have this formula for 1 upon 1 minus beta is equal to MYi divided by MIi. We just inverted it. So now it is inverted form, it is MIi divided by MYy. So here also MIi, and in the other equation also MIi, we have one MIi in the numerator and the other MIi as the denominator, so we can cancel it. So what we are left with, 1 minus beta hat multiplied by beta hat divided by 1 minus beta hat. So this is your 1 minus beta hat and 1 minus beta hat, they cancel. So your beta hat is equal to MCi divided by MYi. This is nothing but your ILS. So we started our discussion on indirect least squares method. We took a structural model and then we got the reduced form. You got the estimates by using OLS of the reduced form, and here we are just algebraically manipulating and we get the ILSE, that is the indirect least squares method. Now let us prove that the beta hat which is being obtained over here by the process of indirect least square method is consistent, and this beta hat, when we estimated without, it's by the simple OLS, we have seen that it was not consistent. So beta hat is equal to MCi divided by MYi, and MCy we can write it as 1 divided by n multiplied by summation C minus C bar multiplied by I minus I bar, and MYi can be written as 1 divided by n multiplied by summation y minus y bar multiplied by I minus I bar. There is again, there is again a mistake over here. In the PPT, for the denominator term MYi, it is written summation y 1 by n summation y minus y bar multiplied by again y minus y bar. That is wrong. It should be I minus I bar, the second term. So MYi should be 1 by n summation y minus y bar multiplied by I minus I bar. Now we can cancel 1 by n, and 1 by n is in the numerator is also in the denominator. So that is, you can write it as summation C minus C bar multiplied by I minus I bar divided by summation y minus y bar multiplied by I minus I bar. Now this we can write it as yt is equal to, so we are writing yt is now we have yt, we know the function of yt is equal to alpha divided by 1 minus beta plus 1 upon 1 minus beta it plus 1 upon 1 minus beta ut. This is the function for it, and we can just write the similar function for y bar. Y bar is equal to alpha divided by 1 minus beta plus 1 upon 1 minus beta I bar plus 1 upon 1 minus beta U bar. So now we can say yt minus y bar, we can find yt minus y bar, and this is equal to yt minus y bar. We have just now written the function for yt and the function for y bar. So y minus y bar is, we take the first term alpha divided by 1 minus beta plus 1 upon 1 minus beta it plus 1 upon 1 minus beta ut minus alpha 1 minus beta minus 1 upon 1 minus beta I bar minus 1 upon 1 minus beta U bar. So now the terms which are highlighted with the yellow color, that is alpha 1 minus beta is plus and minus alpha 1 minus beta. Those terms we can cancel. So what we are left with y minus y bar, what we are left is with this term. Y minus y bar is equal to 1 upon 1 minus beta I minus I bar plus 1 upon 1 minus beta U minus U bar. With this term, we multiply this term, we take the summation and we multiply this term with 1 minus y bar, I minus I bar. So summation y minus y bar multiplied by I minus I bar is equal to 1 upon 1 minus beta summation I minus I bar square plus 1, because we are I minus I bar was already there, we are just multiplying another I minus I bar with it. So we get summation I minus I bar square plus 1 upon 1 minus beta, you have U minus U bar multiplied with I minus I bar. Then we multiply both the right hand side and left hand side with value 1 minus n. So 1 minus n summation y minus y bar multiplied by I minus I bar is equal to 1 upon 1 minus b summation 1 upon n I minus I bar square plus 1 upon 1 minus beta 1 upon 1 minus n summation u minus u bar multiplied by I minus I bar. So this, in terms of moments, we can write it as myi is equal to 1 upon 1 minus beta. This term is written as m1ii and plus 1 upon 1 minus beta. The last term, that is u minus u bar multiplied by I minus I bar, it is written as mui. So this is my equation over here. Now, so we have done for myi. Now for beta, we need mci also, because the formula of beta, it needs both the terms mci and myi. Now C, the reduced form is C is equal to alpha divided by 1 minus beta plus beta 1 minus beta it plus 1 upon 1 minus beta ut. From this we can write it in terms of C bar. C bar is equal to alpha divided by 1 minus beta plus beta divided by 1 minus beta I bar plus 1 divided by 1 minus beta U bar. Now we deduct C bar from C. So C minus C bar is equal to beta 1 upon 1 minus beta I minus I bar plus 1 upon 1 minus beta U minus U bar. This we multiply both the right hand and the left hand side with 1 upon n. So 1 upon n summation C minus C bar multiplied by I minus I bar is equal to beta 1 upon beta multiplied by 1 by n I minus I bar square plus 1 upon 1 by n 1 upon 1 by beta 1 by n summation multiplied by U minus U bar multiplied by I minus I bar. So now we can write it in terms of moments. So MCI is MCI is equal to beta 1 minus beta. This term I minus I bar square is written as 1 upon n I minus I bar is written as MII plus 1 upon beta U minus U bar multiplied by I minus I bar is written by MUI. So this is my equation for MCI is equal to beta 1 upon beta MII plus 1 upon 1 minus beta MUI. Now we take beta hat. Beta hat we have seen earlier is equal to MCI divided by MII. Now you write the equation for MCI in the numerator and MII in the denominator, that is beta divided by 1 minus beta MII plus 1 upon 1 minus beta UI divided by 1 upon 1 minus beta MII plus 1 upon 1 minus beta MUI. Now, so what we do, we take out in the top, in the numerator, I take out 1 minus 1 upon beta as outside, and in the bracket I can write what is left. In the first term is beta M11 from the second term plus MUI. So the numerator becomes 1 upon 1 minus beta bracket open beta MII plus MUI. This is divided by, again from the denominator also we take outside 1 upon common as 1 upon 1 minus beta bracket open MII plus MUI. Now 1 minus 1 upon beta is in the numerator and also in the denominator, that can be cancelled. Again, when n tends to infinity, because n becomes very large, MUI will also become 0. So what we are left with, that the probability limit of beta hat is equal to beta M1, because MUI it has become 0 and MUI in the numerator and denominator they also become 0, because when n tends to infinity that will happen. So the probability limit of beta hat is nothing but is equal to beta MII divided by just MII. So MII is in the numerator and also in the denominator, these two cancelled out. So we are left with probability limit of beta hat is equal to beta. So hence we are proving that the indirect least squares method, the beta hat which we have obtained from the indirect least square method, is the probability limit of this beta hat is equal to beta. So it means that beta hat is a consistent estimator of beta. So with this we are this discussion we have completed our discussion on indirect least squares method. We will be moving to the next method.